Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a problem that is more theoretical than anything else. This is around the second law of thermodynamics and the Carnot engine. And it's a great question to conceptually understand what's going on. It's not a complicated question. I'm going to solve it with you, obviously, but I suggest that you give it a go before you see the solution, because it's not a hard question to solve so long as you understand the main concepts surrounding it. So this is question 6.77, and it reads like so. An inventor claims to have devised a cyclical engine for use in space vehicles that operates with a nuclear fuel generated energy source whose temperature is 510 Kelvin and a sink at 270 Kelvin that radiates waste heat to the deep space. He also claims that this engine produces 4.1 kilowatts while rejecting heat at a rate of 15,000 kilojoules per hour. Is this claim valid? So we start by, the first thing that we're going to note is that this is kilojoules per hour. So we're going to convert that, because we can't really relate kilojoules per hour with kilowatts, because one is kilojoules per second, the other one is kilojoules per hour, right? The second thing to note is that these two guys are in Kelvin, so all good there in regards to its units. Okay, so we have a heat engine. It's taking energy from a heat source at 510, rejecting to a heat source at 270. We know conceptually that the heat engine is limited by these two things, right? By these two things, by the source and by the sink, right? It needs to take energy away from the source and reject it to the sink to be able to produce useful energy, which is the 4.1 kilowatts. Okay, so the first thing I'm going to do is I'm going to convert the kilojoules per hour into kilowatts, just to have the a comparable. So let's just do this as Q, heat being rejected, a comparable unit, right? And this is 15 times 10 to the third kilojoules per hour. And I'm going to note that 1 hour is equivalent to 60 minutes. And I'm also going to note that 1 minute is equivalent to 60 seconds. You could jump this step if you know it's 3,600, but so minutes and minutes go away, hours and hours go away, and we're left with kilojoules per second. Okay, so Q rejected, right, is the same as 4.167 kilowatts, kilojoules per second, kilowatts. Okay, now it's easier for us to have an idea of what's going on. Now, what do we need to know? We need to know that we need to see whether his claim is valid or not. To that, we can check out the efficiency, right? We can check out the efficiency of this heat engine. The efficiency is a measurement between, the output, right? The output of what we're looking for, the useful energy in this case, and the input that's going into our heat engine. But as we know, it's also limited by the source, right? It's also limited by the source. So the maximum efficiency you can possibly gain with a heat engine, according to the second law, is the Carnot engine, right? Carnot, using the Carnot cycle, and that is going to be limited by the sink and the source. Okay, so what we can do is we can see the following, right? We can calculate what is the maximum possible efficiency this guy can have, and then we can calculate what is the claimed efficiency it has. As long as the claimed efficiency, let's actually write that down, as long as the efficiency claimed is equal or smaller, right? Equal or smaller than the maximum efficiency, according to the second law, then his claim can be very well true, right? If not, then we know he is lying, right? This is not true. So we can start with the claim, right? So the claim, what's the claim? The claim is that he can output 4.1? Was it 4.1? I forget. Yeah, 4.1 kilowatts. 4.1 kilowatts. While rejecting 4.1 167. Right, and the total input as you can check the previous video to remind yourself that, oh, actually we can look at this now. Let's look at quickly now. Right, we can remind ourselves that the total energy going into this guy here, the energy balance of this heat engine here, has the Q of the hot source going in, the useful work coming out, and the Q being rejected coming out too. Right, so the energy balance here, first law dictates that QH equals work plus Q rejected, right? So the total energy here, and the input down here, what I've put, instead of putting the input like so, I've put the input like so. Okay, this is where this comes from. Boom. Right, so it's in reverse, right? So let's just reverse this. This is Q rejected plus work. Okay, so obviously units go away and we're left with the ratio, which is the efficiency, and we get 49.6, right? So 49.6%. Okay, and so far so good. We don't know whether this is possible or not. There's nothing wrong with that number per se. It could be higher, but what we need to check is, what's the maximum possible. And here we can check with this, right? It's going to be 1 minus the sink. The sink we know to be 270, right? 270 Kelvin, and the source is 510 Kelvin as well. Okay, notice that how the Kelvins go away, and we're just left with a ratio that's going to subtract 1, which is 100% efficiency. By the way, before I do this math, just note the following, right? Note the following. For this to be 100% efficient, what we needed is for this whole guy to go to 0. How can we do that? Well, if we have a sink that is at 0 Kelvin and it can take as much energy as we can possibly throw at it, or this bottom guy here going to infinity, right? So if we have a source that is at infinite temperature, has infinite energy. So, good luck finding that. Let me know if you do. I would love to share the engineering to hack that out and, push society forward. So this gives me 47.06%. And how does it compare? Well, how does it compare? Ooh, check it out. Check it out. We have a maximum possible efficiency according to the constraints of the second law of 47. And his claim is that he can get 49 out of it. Okay, so we can say very confidently that the inventor's claim is not valid, right? Because it violates the second law of thermodynamics, right? The claim states that we have a 49.6% thermal efficiency when the maximum achievable under the given conditions is 47.06. Okay, so like I said, this is not, a hard question to solve in terms of numbers and the things we need to input, but it isn't an important question because it requires you to understand this idea here, right? And to be able to relate the things that are being said back to the idea of the first law, to be able to come up with this energy balance here, and then the second law to understand that it's limited by the sink and the source, right? So I hope this helped you out. This is a useful exercise. If you didn't do it before on your own, maybe try doing it again and seeing if you understand it better. If this video helped you out, considering liking it. If you have any questions, just leave them down below in the comment section, and we'll talk soon.